Hello, this presentation is about fast and low-cost mitigation for ReRAM variability for deep learning applications. My name is Jong Lee from UNIST. A ReRAM crossbar array or RCA can be extremely efficient because it consumes very little silicon area and because it also has extremely high parallelism. However, the problem is computation accuracy. Typically, we use RCA to do MVM or matrix vector multiplication operation, where weight matrix is mapped to ReRAM conduction values. So if ReRAM conduction value is somewhat different from what you intended to be, the result of the MVM operation will also be different. That is how variability can distort MVM output. And there are multiple types of variability, and the program variability or write variability or the read variability or read disturbance. The previous work to mitigate a variability problem or in general, many non-ideality problems can be classified into either online or offline methods. Online methods are basically simulation-based methods, such as retraining. Offline method is simple because there is no actual hardware involved. But since it relies on a non-ideality model, its accuracy depends on the accuracy of the model. That is why offline methods are ineffective against certain types of variability, such as programming variability. Online method, on the other hand, uses the actual hardware output. An example is on-chip training, which is of course very expensive. So in this work, we propose an online method, but it does not rely on any training data. Our method does not perform or require any backpropagation. And in fact, we do not do any training of the model and does not update weight either. So our method is a very low-cost method, and we propose a simple hardware architecture as well as an analysis on why and when it can be effective. The main idea of our method is that instead of full retraining, we can just do readjusting of the activation values, actual activation statistics, which can be very helpful in reducing the effect of ReRAM variability. So this can be achieved through batch normalization layer, which are very common these days, especially for low precision networks such as binarized neural networks. A batch normalization layer performs three distinct functions depending on whether you're doing inference or training, or whether you're doing forward or backward pass. In the forward pass, which is the only pass during inference, BN layer does what we all know. It just computes Y using the mu and sigma parameters. For training, there are two passes. In the backward pass, you will update the batch norm parameters, beta and gamma. This is where backpropagation is needed, and you also need training data for that. However, in the forward pass, you update mu and sigma, which are the mean and standard deviation of input x from the current batch statistics. So we call this function statistics update or stat update. And stat update does not need backpropagation or training data. You do need some input data, but it doesn't have to be labeled, so it is very cheap. We call our scheme a batch norm calibration or BNC. So we have a more detailed analysis in the paper, but this slide quickly explains why our BNC method can be effective. So in the original network, you do batch normalization, and the output goes to other layers such as convolution to get the final output. But the variability in ReRAM crossbar array distorts the RCA output, causing some discrepancy in the final output. So our BNC method does not change X directly, but adjust mu and sigma so that the output of BN layer have the same statistics as that of the BN layer before variability. So this is our hardware architecture. The important point here is that we do not need to do this calibration on every inference run. It is a calibration, so it needs to be done only once in a while, like initial programming or whenever you update the weight. Our state update function can be implemented in software running on the main processor, so there's almost no hardware cost. So in order to do this, we need to access both input and output of the ReRAM crossbar array, which can be done through scan chain registers, which are there anyway for testing purposes. So here's our experimental setup. I just like to point out the schema P parameter here is for the programming variability, and we also vary the global and local variability. So here are some of the results. The schema P parameter here is varied from 0.15 to 0.3. The greater the schema P, the higher the variability is. Y-axis is accuracy, and the blue graph is the inference accuracy without any calibration. The orange or the red graph is a batch mean calibration, which is kind of similar to previous work. The green is our proposed method. So as you can see, the blue graph shows that the inference accuracy without calibration degrades very quickly as we increase variability, whereas using BMC or BNC can recover most of the accuracy degradation. More importantly, our BNC method is more robust than BMC, and in all cases, we see that BNC outperforms BMC. In some cases, the difference between BNC and our BMC is very high, as you can see on the right graph. So there are more graphs than results in the paper, but overall, our experimental results show that the BNC is more robust and works pretty well in many cases. So to summarize, we presented an online method to mitigate the effect of ReRAM variability. Even though our method is an online method, it does not require any training data or costly backpropagation, but only adjust for the parameters during a process called calibration. The calibration process can be implemented in software, therefore it has very little hardware overhead. Thank you for listening.